Welcome to today's webinar titled How Aerion Technologies Generates Aerodynamic Databases with Hydra, a framework in Python using Cart3D, GoCart, and Tecplot.
We have two panelists today. We have Matt McMullen. He's a senior aerodynamicist and product manager at Aerion Technologies and oversees the development of simulation and analysis software, focusing on specifically high-speed aerospace vehicles. We're very happy to have Matt with us today. And myself, my name is Scott Fowler. I'm product manager here at TechPlot. I've been in this role for about a year and a half now and have been with TechPlot since 1999, so quite a tenure here so far. My job is to really understand where the CFD and aerospace markets are going and gather customer feedback and make sure that we're building the right tools for you to get your job done. So our agenda today, we're going to briefly discuss some of what TechPlot has been up to this past year and describe some of the new technologies that we're working on, particularly Tecplot 360 and Tecplot Chorus, which you'll see how Aerion is making great use of today. Then we're going to hand it over to Matt, and he's going to give us an overview of the Hydra framework, which he's developed in Python and using some of the technologies that Aerion has been working on. Matt is also going to give us a product demonstration. We're going to go over a mock and alpha angle of attack lattice, and he has a couple of other interesting examples to show us today as well. And then we'll finish it off with some quick conclusions and then open up the floor to questions. I'll give a quick introduction to TechPlot and who we are. We've been in business for 35 years now. We actually started as a CFD solver company back in the 1980s, our roots being in aerospace, founded by a couple of Boeing engineers who decided that they'd rather work for themselves than work for Boeing, and they've built a great company here. In 2001, we transitioned full-time from CFD solver solutions to data visualization. And since that time, we've really been focusing on our primary product, Tecplot 360, to help people who are working with CFD and to analyze and visualize their results. So a quick introduction to our two primary desktop products. We have Tecplot 360 EX. It's a visual data analysis tool that improves your productivity. We're fairly unique in the market in that we have integrated XY, 2D, and 3D plotting. We've also been spending a lot of time the last year or two working on performance. Our current release is over 2 times faster overall than our release in 2013 due to a lot of parallelism that we've taken advantage of and some file format improvements that I'll discuss in just a couple of minutes. We've also been working on another product called Tecplot Chorus, which you'll see Matt is taking great advantage of in his aero database work. This has really been designed to help people who are doing aero databases and who are doing optimization studies. TechPlot is not just a desktop technology company. We also have developer solutions. I view us as a company who is really trying to enable people who are doing simulation and in particular CFD, and we have these other tools available. TechIO is a library that allows you to read and write the TechPlot binary file formats, and just last year we released an MPI version of the TechIO library. So if any of you out there are writing CFD solvers and need to run on a parallel architecture, that's available to you. Another thing that we've realized is that we really cannot tailor our desktop products to everyone's specific workflows, and so we've released a couple of other customization tools. Tecplot ADK allows you to customize Tecplot 360's UI. We have that available in both C++ and Fortran. And new for 2017 is a brand new Python API that we're calling PyTecplot that allows you to automate Tecplot 360 capabilities. We're very excited about this library that's coming out. You can see a little snippet of example code there. It should be pretty easy to pick up and use. The last bit of technology that I'll talk about is subzone load on demand, or sizzle. This is an enabling technology for us that first manifested itself as a data file format. The idea here is to be able to load very large grids with a very small amount of memory, and also load them quite a lot faster. We found in recent years that the primary bottleneck in CFD post-processing has become the disk. The disk I/O just cannot keep up pace with the rest of computing. So until Seagate and other companies like that figure out how to make their disks a lot faster, we're going to be contending with a disk I/O bottleneck, and subzone load on demand technology enables that. So again, why are we working on these technologies like subzone load on demand, like Tecplot Chorus, and increasing the speed of Tecplot 360? Well, we noticed some trends in the CFD market. Starting around 2010, we started seeing these trends, and they were recently confirmed by NASA when they released their CFD 2030 vision paper in 2014. If you see the knowledge extraction line, which I'll zoom into here, the NASA CFD 2030 vision is predicting that by about 2030, we're going to have cell models on the order of 10 to 100 billion cells will be commonplace. They're also expecting that engineers are going to need real-time processing and display of many high-fidelity CFD solutions. So that's one of the driving factors for Tecplot Chorus. And they're also going to have to be able to merge the high-fidelity CFD simulations with other aerodynamic data, such as wind tunnel and flight test data. And again, Tecplot 360 is very good at bringing in both the simulation data and the experimental data. So we really see the market going in two directions with the advent of the ubiquity of HPC resources. Grids are getting larger, and people are producing more of them. And so that's why we have Tecplot 360 for the large grids and the sizzle technology, and then Tecplot Chorus to help people who are doing lots of simulations. Just a quick sneak peek to what's coming in 2017. We are going to have another release of Tecplot 360 available in January. For the Cart3D users out there, we're going to have a native loader for the Tricks file format, which comes out of Cart3D. Tecplot Chorus is going to be bundled with Tecplot 360 now, so everybody is going to have access to some of the capabilities that you're going to see Matt demonstrate today. Like I mentioned earlier, PyTecplot is our Python API, which will be released at the turn of the year, and very exciting for us. We're leveraging that sizzle technology, the subzone load on demand technology, to also create a client-server type architecture. So this is going to give you remote access to your data using the sizzle technology. So with that, we'll go ahead and pass it over to Matt. Let me unmute you here, Matt, and change presenter. And we're going to learn about how they're using Hydra and the Tecplot technologies to help with the aerodynamic databases. So let me just presenter is you, Matt. Take it away.
Thanks, Scott, for the introduction. I want to thank everyone in the audience as well for attending today. Hopefully we can all learn something. Hopefully you guys learned something a little bit about Hydra, which is the tool that we've been developing here at Aerion Technologies to do this aero database work. So hopefully everyone is looking at my title slide, and off we go. Wanted to start with giving an introduction, or at least an overview of what I'm going to be talking about today. First, we're going to introduce the concept of what an aero database is and discuss the workflow used in its construction. And then we're going to go through a demonstration of the basics of Hydra and how to go through that workflow to construct the aero database. We're going to illustrate that workflow using a mock alpha lattice demo. We're going to highlight the interaction between Hydra and Tecplot 360 and Chorus, ultimately to allow the user to view the solution of the database, or a large number of solutions simultaneously within the database for the purposes of comparison and quality assessment of the database. And then we're going to go in and show some advanced features within Hydra, show some results that have been pre-computed from other databases that we've worked on. And then finally kind of discuss a little bit about future work associated with the product. So let's get started. Obviously, Hydra is our utility that facilitates the generation of aero databases. Aero databases are typically defined as a large number of CFD runs which brought together define a response surface. The response surface ultimately predicts some measure of the performance of the aero performance of a vehicle, either over a range and operating conditions such as Mach number and angle of attack, or range and design variables, and those things could be maybe a parametric definition of surface OML. Common aero databases, you see them all the time in the aerospace industry. They include performance databases like lift and drag pollers that you've seen for years. But other things are like, you can see other databases like handling quality databases, where people are looking to assess or quantify basically forces and moments for the purposes of establishing the stability and control of the vehicle. Finally, you also see a lot of loads databases being done where pressure distributions over a variety of operating conditions are integrated together over panels, structural panels on the vehicle, and these basically provide load inputs for the structural mechanics solvers for the purposes of assessing the worthiness of the vehicle structure. Cart3D is a flow solver that is a workhorse in this space. It was written by Mike Aptimus and Marcia Berger at NASA Ames. It is an invisive Cartesian mesh flow solver which employs shared memory parallelism today. We also have a version that has a distributed memory parallelism that we'll be supporting in the not-so-distant future. Its two claims to fame are it's a particularly robust flow solver, and secondly, its mesh generation is roughly independent of the geometric complexity. And when you couple those two things together, you get a flow solver that is particularly good for this type of environment. In other words, there's a very low probability ultimately that the flow solver is going to crash. And when you're doing thousands and thousands of cases like that, even with the geometry of the OML varying or the operating conditions varying, and you're running into a dramatically different types of physics that are being exhibited throughout the individual solutions, these two characteristics provide for a very robust computational framework. As everyone knows, Cart3D lacks the viscous effects associated with a modern-day Navier-Stokes solver or a RAND solver. But aero databases typically are less interested in highly accurate point solutions. So for example, when one approaches maybe a loads database, there is a significant amount of conservatism in the factors of safeties that are employed after the fact. That and the loads themselves are more a function of the pressure forces and less a function of the viscous or shear stresses. And so the application of an Euler solver in this environment is advantageous, given that it's significantly less costly than a full-up RAND solution. As well, a lot of sensitivity studies are more interested in generating trend information, and the trends, again, are more functions of the pressure terms, and the trend information is, well, the effect of the viscous forces on the trend information is of the second-order effect. And again, given the cost ratio associated with generating an Euler solution, and given the number of solutions ultimately that one needs to run for large databases, people find themselves going to a lower fidelity method and using that over a RAND solver in this space. Wanted to talk a little bit about the demo that we're going to be showing a little later, just kind of introduce the concept of what the geometry was and the experiment that we're going to run that will comprise the database. Specifically, we're going to compute a Mach alpha lattice, which is kind of what I would call a granddaddy of aero databases. It is the permutation of all the Mach numbers and angles of attack and the vectors listed there. In this particular case, it would comprise a set of 25 different cases. We're going to do this on a target drone geometry that's shown there at the bottom. Obviously, this isn't a real geometry, but the physics that are present on this geometry are comparable to those that manifest themselves on commercial or military geometries that typically people are doing this in industry or academia. And the nice thing about the geometry is that also we've genned up some control surfaces on this, so we should also be able to support some aileron sensitivity studies, which will show results from later today. So let's talk a little bit about the workflow associated with doing these types of databases. The first thing when asked to do this, people typically sit down and establish what I would call a template calculation or workflow or process. And that template is basically the collection of all the data and commands that uniquely define the process to compute a single solution. And to establish a template, what you're typically doing is subsampling the set of all operating conditions that are in the database, trying to find some representative operating conditions, and basically testing your theories about what collection of command line options need to be present in the solver, or I should say options that need to be present in the solver ultimately to ensure that the solver will yield a good result, not only at the representative operating conditions upon which you're testing, but also over the span of the database that is of interest. And that vetting process to establish the template is kind of iterative. One goes back and forth looking at the quality of the solution, changing mesh resolution or flux functions and limiters and blah, 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 until finally the user is happy with the results at the representative conditions. And then one basically clones that template over all the other operating conditions within that are requested by the database. And that process, which is the creation and management of the database, is where Hydra comes in. Hydra does the process of cloning the data, which is propagating the setup files for all the cases, and executing the kernel of operations for all the cases. In this particular case, executing the flowcart executable itself, but also all the mesh generation stuff or any other utilities that might be needed in advance of that. Hydra also allows the user to monitor the status of all the runs and restart specific runs, and it facilitates people working not only in their local machine or via queuing systems, which would allow remote execution, which is common because the size of these databases is typically quite large, and running this on a laptop or desktop is not a good idea. One also would like to, and Hydra supports this, quickly and easily propagate post-processing templates over all cases in the database and gather them back into a central repository such as Chorus to allow for a quick juxtaposition of solutions. And moreover, there's going to be a large number of different data files that are produced as the process evolves over the database, and ultimately one wants to scrub results out of these data files and bring them back into a single file with a single with an easy to support interface that will allow you to basically export this data to other software, say Microsoft Excel, wherever you ultimately want to use the data. So let's talk a little bit about the establishment of a template, which is the basis for all of the calculations that go throughout the database. There are two ways one can do that. I'm going to show you today a way to do that through GoCart, which is a UI tool that we have developed here in-house. I'm showing you right now, you should see a picture of a target drone geometry with a flow solution. You should see pressure coefficients superimposed on the geometry for a representative operating condition within the Mach alpha lattice. I think this is alpha 0 Mach 0.8. But GoCart allows you basically through the UI to define all of the parameters associated with running flowcart, or at least all of the parameters associated with running the pipeline of utilities that produce a Cart3D solution. That's not only flowcart, but it's also the volume mesh generator called cubes and mgprep, which is the multi-grid hierarchy. mgprep establishes a multi-grid hierarchy of grids for the convergence acceleration utility inside of flowcart, and also auto inputs, which defines the domain of interest ultimately upon which you're solving the equations of motion. So one can walk through this UI, start messing around with the application of boundary conditions or CFL conditions, as you see here, or flux functions, and run solutions inside of GoCart. I'm not going to show you one today. It'll take a while on that. And then do post-processing within GoCart as well, can look at the solution here and look at various aspects of the solution, like this is the X component of velocity, density, Mach number, blah, blah, blah. As you assess the quality of the solution, you go back and forth within the different menus of GoCart, changing parameters, maybe changing mesh resolution. And at the end, you can export a JSON file which looks like what I'm showing right here. And basically this captures all of the key value in a key value pair format, all of the values that uniquely, all the data elements that uniquely define the pipeline of commands to produce that flowcart solution at that operating condition. That's the template we've been talking about. Another way of getting that template is to use a Cart 3D command line workflow, and this is how I learned Cart 3D. It's probably not the way most people would feel comfortable using it, but you can sit down on the command line and type out the names of the commands ultimately to produce the individual files that are ultimately piped into flowcart, which are responsible for setting up, like I said, the domain of interest, the volume mesh, the multi-grid hierarchy of grids. Each one of those commands leaves an artifact or a file in the directory, and we have scripts which will basically scrub those files and recreate a template JSON file that I'm showing down there below after the fact, after you've gone through that process itself. So hopefully one doesn't find themselves sitting in a command line with a text editor trying to edit these files. Hopefully one uses GoCart or an automated tool like Cart 3D Services provides it to generate these template files, and doesn't have to go through that process. So now you have a template, and you want to figure out how to take that template and create a database out of it. And that comes in the design, and here comes the design of the experiment, or the DOE file. This DOE file I'm showing here is shown in the yellow block there, shows the very simple experiment that we've discussed already, which is the Mach alpha lattice consisting of 25 cases. The DOE file is comprised of 3 lines. The first one, cart3dservices.json, which is the name basically of the template file that we're going to use, and then it says I want to vary the key value. I want to vary the key inside of that JSON file, the flowcart alpha key and the flowcart Mach key, using the discrete floating point vector, using the discrete values shown in the vectors there to the right of each of those keys. And it basically creates a lattice of 25 cases by permuting each one of those values. Note, there's only 3 lines of code in this, 3 lines of text in this particular file. And so Hydra, we designed this file so that you wouldn't be typing in a lot of things like specifically naming executables to be run. Hydra is deducing ultimately that the cart3dservices.json block means that the user wants to run the Cart3D Services application. So there's a naming convention that is being employed in the file to make things more simplistic. However, people oftentimes want to run more advanced DOEs where they're chaining together multiple commands for each individual case. And we do support that as well. And we're going to show some design studies and an aileron sensitivity study later in this talk, which will show how one does this inside of this file format. So I've got my template file, which defines the individual case. I've defined the design of the experiment, ultimately, that will comprise the database itself. I want to now go to Hydra and run some commands inside of Hydra to create this database. And so here is a list of the files that one would use to do that. I'm sorry, here's a list of the commands that one would use to do that. The first thing you would do is type in init, and that will initialize the Hydra project. Then you'll type in launch, and that will basically create the directories and case files and launch all the cases in the database. There's some status and dir commands, which will allow you to assess the progress and convergence statistics for the cases and display links between the case directories and the parameters used to find the case. One can also restart to rerun specific cases in the event that things fail. The post-process command allows people to propagate Tecplot layout files, collect data, and automatically launch Chorus at the end of that. Like I said, there's an interface with the SGE and PBS systems, so one can specify the queue system ultimately to run on, or if you specify none, to run on localhost. And there's also some configuration associated with Hydra to allow a customization of commands, and so there's some config options as well that are supported. You'll notice as I go through the demo that Hydra has a Git-like behavior to it in the sense that after you run the init command, you can run any one of the Hydra commands within the project directory structure, and it doesn't care from what working directory, as long as you're within that hierarchy that you execute those commands. Excuse me. So let's launch something here. Get out of this. I'm going to go over to a VM that I have running on my laptop here, and let's run this mock alpha lattice. I'm showing here what you should see in the terminal here is more on two different JSON files. We're going to run a very small JSON file here today, we're going to run a very small JSON file here today because I'm running on a VM. Because I'm running on a VM, I don't necessarily have the computational horsepower to run through a large number of cases in the time for a demo. So I'm going to run the DOE demo.json file as basically our DOE over a template that's defined here as cart3d surfaces.json. And the parameter key, and I'm showing that right now. So what one does is simply type in Hydra launch, I can type DOE demo, hit return, and automatically you see that it's creating the following directories. And if one were to sit here, I'm running this on localhost, so if one were to execute a top and look at the processes as they pop up, I should see 9 instances of auto inputs which define the domain of interest. I should see 9 instances of cubes pop up, which define the volume mesh, 9 instances of MG prep, and then 9 instances of flowcart to compute the final flow solution. All of these things cycle through, and what it's doing is creating basically a case structure that looks like the following. There's a project directory, which we were originally in, and then there's an experiment directory in this particular case called DOE demo, which contains all of the case directories which hold the case-specific solutions, and they're identified as integers there in black. And in this particular case, there'll be 9 case directories which are created. There's also a .hydra file which is created when if one were to type in the init, which holds the configuration-specific files. So obviously one wants to assess the status of the runs as they're executing, and so we've put together this status command, and we worked a little bit on this command so that you get the very simplistic figures of merit that you can quickly and easily look at to assess the overall quality of the database. And the two that are used are this residual ratio, which is basically the log of the final residual to the maximum residual. The more negative the number is, the deeper your convergence. And you're going to see some force and moment statistics also computed, not only mean but standard deviation computed over a window in the last 20 multi-grid cycles for each calculation. And that will give you, or at least it will quantify the variation in the forces and moments, or each component of force and moment, and give you an idea of how the functionals are moving with respect to, or varying with respect to, ongoing application of multi-grid cycles in the process. So let's go back over to my VM here. I simply type in Hydra status DOE demo, and up pops this little matrix. And so the case numbers are on the left there, 0 to 8. So there's 9 cases. It tells you the iterations that were completed for each individual case. Flowcard, if you reach a specific residual criteria, will automatically stop. So not all of the cases ran to 150 iterations. This is a particularly small case that I ran. I set the mesh, if you were paying attention and saw in the DOE demo.json file, I set the mesh resolution to be particularly coarse, allowing a very deep convergence of the residual. And that is, you can see that in the residual ratios for both the infinity norm and the L1 norm of the residual in the 3rd and 4th columns there. You're typically getting 8 orders or 8 decades of convergence in the infinity norm, and 6 or 6+ decades in the L1 norm. And then you see before some moment statistics in the subsequent 6 columns there. Each column has an average and a standard deviation, and all of them are scaled, if you see at the bottom, by a common coefficient. That allows, as these forces and moments in many instances vary significantly over the entire database, but when you commonly scale them like this, you have a very good idea of the variability of one case relative to any other cases in the database. So it is a very quick and easy way to assess convergence quality of your database. Back to my slides here. So you'll notice that each individual case directory has an integer number associated with it, and that is good because it's a simple format that people can easily parse, and it's flexible to admit any number of different naming conventions associated with parameters. But it's bad because people don't necessarily know what the contents of each individual directory is. So we wrote a utility or an option within Hydra to provide that link between the individual case directory and the unique parameters ultimately that were used in the computation of the directory itself, or the creation of the directory itself. So one just types in Hydra dir, and up pops this little matrix here that says my directory name is Home McNew TechPlot Webinar DOE Demo case number 0, and that corresponds to Mach number 0.5, angle attack 0, and all the other cases are listed as subsequent rows in the matrix. So let's get to the part that I think everybody is really interested in, which is how we work with Tecplot, specifically Chorus. The Hydra post-process command allows provides the ability or capability to work directly with Chorus. It, by default, Hydra provides a set of macros to generate residual force moment history plots. And basically what these are those quantities, residual force and moment, as a function of the multigrid cycle used by Flowcart. We use these constantly in the field, ultimately to assess or to look at the variation of these particular quantities as a function of the multigrid cycle, trying to again assess convergence of the solver. Users can also, though, define graphics, custom graphics to be generated besides the default ones that are provided by simply dropping in a layout file into the project directory, and the post-process command will clone that layout file all over the database, and it will collect the graphics associated with that. It will also scrub the integrated quantities that are provided in the loadcc.dat file and pull them all back into Chorus, which it automatically launches at the end of that process. So let's, and at the bottom of the screen, I'm just showing two quick Chorus examples of Chorus post-processing some results, but let's go through and show how this physically works. I'm going to step out of, I'm going to run this Hydra command on a pre-computed experiment that I'm calling DOE right now. The reason why I'm doing this on a slightly different experiment is because the mesh resolution associated with this experiment is much greater, so the quality of the visualization products are going to be superior. This is also done over a larger number of cases. Like I said earlier, I'm running this on a small virtual machine on my laptop right now, so I don't really expect that I can get a lot of throughput. I can handle a large number of cases on a setup like this. I will say that I have a 24-core desktop machine sitting on my on my desk, and I rarely wait a significant amount of time to do 300 or 400 to the generation of 300 or 400 graphics that comprise some of the databases that I'm working with here. So this is going to take a little time. As you see, there's it's kind of a status menu that's displayed as Hydra is propagating the different Tecplot layout files throughout the extent of the database, and then automatically Chorus pops up, and this is just the default screen that one walks into in Chorus. So I'm going to click on the matrix view of the images that were produced by this, and the first thing you see are the force moment and residual plots that I discussed that Hydra generates by default. One can come down here and click on, the force plot is here, the moment plot is here, the residual plot is here. You can zoom in and scroll through this database and start comparing convergence histories graphically between different cases that were computed in the database. And this is extremely powerful. It's more powerful than the statistics that I showed earlier, in the sense of giving the operator, the creator of the database, an idea of exactly physically what's happening with the convergence of his solvers over a multitude of different cases. And they're doing it very, very quickly. Like I said, Hydra also provides for the support of custom layouts, and so if one were to, I didn't show it, I left a layout file in the project directory. This is something that I laid out a little bit earlier. I call it surfacecp.lay, and it shows contours of pressure coefficient of the vehicle. I just put that into the project directory, and when I ran the post-process command, Hydra automatically propagated that layout file and generated PNGs for every case in this database, and then automatically gathered those PNGs back into Chorus, and this is exactly what you're seeing right now. The columns are at constant Mach number, the rows are at constant angle of attack, and again, you can quickly and easily peruse all of your solutions using the Chorus tool, again, and try to assess the quality of your grid, how well you're capturing shock structures, and other flow features ultimately that you hope to be exhibited in the results. So, terribly neat, quick. Hydra also scrubs most of the functionals that are reported in the loadcc.dat file. So one could come up to the 3D scatter plot here and plot, let's say, lift coefficient as a function of Mach number and angle of attack. Come in here as well, quickly and easily define a surrogate model to be fit to the data, and then superimpose that on the discrete data, and that's here. So pretty easy and neat to define a response surface with a minimal amount of time associated with that. Another great feature is to come in here as well and to start looking at line plots. I'm going to plot lift coefficient again as a function of angle of attack, and I'd like to group the data by Mach number. And basically this shows me my lift curve slopes at various Mach numbers for this vehicle. Again, I did it amazingly quickly using Tecplot Chorus. So terribly neat, terribly empowering. It's a great utility. So that kind of ends the demonstration on the Mach Alpha lattice. I've got a couple more minutes here, and I wanted to show results without actually computing them in front of you. I wanted to show some results from a design study where we're going to be varying a geometric design parameter on a supersonic wing body geometry. And then I wanted to kind of show how we do or can do aileron effectiveness surveys here as well using using the target drone geometry that we introduced earlier. So we have a tool in-house. Aerion Technologies developed a geometry tool called SAGE. And this allows for the parametric definition of aircraft geometries using a CAD kernel that affords one interoperability between the SAGE tool itself and a variety of CAD systems. And it's a particularly powerful tool for doing conceptual and preliminary design, in the sense that users can define parameters like sweep or span of the wing and quickly regenerate surface triangulations or OMLs upon which to run flow cart calculations to assess the sensitivities of the vehicle performance relative to those changes. In this particular example that we're going to be showing, I've got a simple supersonic wing body geometry with a biconvex wing and a Sears hack fuselage. And I'm simply looking at wing twist. The initial geometry is what you see in the lower left there, and I'm twisting it a little bit. And from the side view that you see there, the rotated geometry has it looks slightly different. You can see the twist or the rotation upward in the base cross-section of the wing. This implies ultimately that I'm running multiple executables for each individual case. I'm running SAGE, and the output from SAGE, our geometry kernel, is a tri-file which ultimately then is input into FlowCart Alpha, into Cart3D services to do a FlowCart calculation. SAGE requires 3 different JSON files, which are shown in the first 3 blocks of the DOE file that's shown in the yellow there, and then Cart3D services.json is the final block that's identified there. Ultimately, what we're going to be doing is rotating one of the sections at various pitch angles, 0, 1, 2, 3 degrees, and then running Cart3D services at 0, 2, and 4 degrees, permuting all those values basically to create a database, a 2-dimensional database. The results of this process look like this. This is a collection of PNGs that were generated over the course of this database. The columns are constant angle of attack. The rows are constant pitch. You can see as one varies the twist, the strength of the shock emanating off the lower surface, and the extent of the expansion region on the upper surface change as the twist of the wing is varied. And you can see that effect directly in the pressure distributions that are shown here in the cut and those that are on the surface of the vehicle. So it's a neat way of quickly assessing what's happening with your flow solution over the course of the database. As well, like I showed earlier, you can quickly and easily pull in various figures of merit that you're interested in. Obviously, the drag force of the vehicle is something that I think people are interested in. You can plot that in a 3D scatter plot, or as well you can pull in a different figure of merit, maybe the lift of the vehicle, and plot that again as a function of angle of attack group it by the pitch angle of the root cross section, and that's what we're showing right here. So basically, as we pitch up the root cross section, we're shifting the lift curve by an amount, and that's what this plot shows. You don't always necessarily want to go back to modifying the parametric definition of the geometry. Many times users want to quickly and easily rotate or manipulate the triangulation itself. Aerion has a set of tools to do just that. One of them is called a rotation tool, and it allows designers or analysis people to rotate subassemblies, watertight subassemblies within a geometry for the purposes quite oftentimes of doing control surface sensitivity studies. So this is kind of the final example that I'm going to show today. It's the target drone geometry, and I want to basically look at how forces and moments in the vehicle change as the aileron ultimately is rotated. So the initial geometry is shown there in the bottom left, and the rotated geometry is shown on the right. And we're going to rotate those geometries over a variety of conditions ultimately and compute flow cart or provide flow cart solutions at each one of those operating conditions and quantify the forces and moments for each one of those cases. So how does one do that? Again, here's the DOE file shown in yellow. It requires running 2 executables for each individual case. First the rotation code, and then the Cart3D services code. The first block is the rotation code, obviously, and it's showing the list of left aileron rotation angles over which that are going to comprise this database. Obviously, there are 2 ailerons in this particular case, and I would like their movement to be correlated with one another. This kind of mimics a flaperon schedule. And so there's a concept inside of Hydra that supports this called parameter linking, where I can make the right aileron basically move in concert with the left aileron. And that's what you're seeing there in that subblock within the rotation.json file. As well, I'm going to move the left flap from its default location, and I'd like to have the right flap move as in concert with that. In the end, this will be a 2-dimensional database of left and right rotation angles at 0, 0.05, and 0.1 radians, and those conditions will be permuted with 4 different angles of attack that FlowCart is running at to give you a database of 12 total calculations. So let's show the output from that. Again, this is the target drone geometry that we were playing around with a little bit earlier. I've got some custom graphics that I pulled into Chorus. You can see a cut plane here. You can see the flow solution pushed onto the triangulation itself, and one can see as one increases the camber of the tip of the wing by rotating the elevator downwards, you can see the change in the flow solution that one would expect. As well, very quickly and easily, you can create response surfaces, multidimensional response surfaces that we demonstrated earlier, and pull in results. This is a lift curve slope as a function of the rotation. This is lift as a function of angle of attack grouped by the rotation angle. So now all of a sudden I can figure out what the lift curve slope is as for each set of rotation angles that were ultimately computed. I think that brings us to the end of the results. Hydra is a pretty small tool in a much larger framework of optimization and design utilities ultimately that we're providing here at Aerion. Hydra will ultimately be included in that framework. which will include response surface and gradient-based optimization methods to allow designers to do very complex optimization design analysis workflows. We're also going to work in the short term, in the near-term future, providing Hydra with a more expansive list of experiments that ultimately, or patterns that ultimately that it can support. Lattices are particularly costly in higher dimensions, and so we're going to implement some adaptive and non-adaptive designs to allow Hydra to search through design spaces a little bit more efficiently. And hopefully that will also include uncertainty quantification estimates. One of the neat things about FlowCart is that it has an adjoint-based mesh refinement capability, which will basically quantify the error associated with the mesh, and it is particularly useful. It would be particularly useful to leverage that in computing high-dimensional databases, such that one could ultimately compute less costly flow solutions in specific directions of the database to minimize the computational cost of that database. We're also going to support, you see a lot of JSON files in this process. We're going to add support for XML files to support the vehicle sketchpad community, and we may look at developing a UI for to allow people to define custom kernels for each individual case in a manner that's kind of consistent or similar with Pedo-based utilities that you see on the market right now. And then finally, we might allow Hydra to quickly and easily access remote HPC clusters maintained by Aerion to afford the user community a surge computing capability. Oftentimes when one is generating large aero databases, the resources associated with doing that work is much larger than what is provided in-house, and so having some third-party support to offload some of the computational effort is needed for a lot of people, and Hydra could support that. And I think that brings me to the end of my presentation today. I do appreciate everyone's attention, and I think it goes back to you, Scott. Thank you.
Thanks, Matt. Yeah, I'll just take control back here and put on a couple of final slides, and then we'll jump into questions. So hopefully you should all see my screen now with the announcement that both Aerion Technologies and TechPlot will be at the AIAA SciTech show in Grapevine, Texas. I think that's the second week of January 9th through 11th. So if you have any additional questions that we aren't able to answer here today during the webinar, or have any other interest, please stop by our booths there. You can also see our email addresses there, and feel free to contact us directly if you have any additional questions or comments. So with that, we'll jump into questions. So you should all have a questions pane on your GoToWebinar sidebar there, and it looks like we already have a couple of questions coming through. So Matt, this first one looks like it's for you. Is Hydra a commercial product, or is it solely used by Aerion internally?
We distribute a lot of our design and optimization products to the community at large. We use them in-house as well, but Hydra is part of is one of the tools that that we provide as part of our distribution. So the shorter answer is Hydra is a commercial product, and you can use it outside Aerion.
Okay. And then a follow-on question to that, when you said about the HPC resources, you said that maintained by Aerion for the remote HPCs. Do you also intend to support public cloud resources like AWS, Azure, or Rescale?
That's a good question. I don't know exactly how we're ultimately going to do all of that. It's on the to-do list. I think that would be I think supporting the alternative HPC platforms would probably be a good idea in the end. It would provide people with the flexibility ultimately to do this on their own, should they want to. But with that comes the overhead ultimately of them having to establish all the codes on the servers that they want, they want to compute on, and so there's a downside to that as well. Whereas if it was an Aerion HPC cluster, you could simply redirect the cases that you wanted to compute to that cluster, and it would automatically be populated with our software on it, guaranteed to run.
Looks like there are a couple of questions about Chorus, which I'll take. Would Chorus also be able to run a DOE or optimization, or is it primarily used to visualize and assess databases generated with a different tool like Hydra? Yeah, at this point, Chorus is designed to pull in data from other sources. So Tecplot Chorus does not perform DOEs or optimizations itself. We do have a capability in Chorus that we call custom actions. There's which you can read more about in our documentation, which allows you to customize some of the things that Chorus can do through a simple registration of a script or an executable that is to be associated. Can you export the response surface from Chorus for later use in a different setup, say running it in batch mode for quick assessments? So when Matt was showing those Kriging surfaces, you can right-click on those and export the data points that make up that surface. So it doesn't export the entire form of the surrogate model, but you can export the surface. We do also have a quadratic response surface, and you can export the coefficients of that as well. At this point, Chorus is fairly limited for scripting, so batch mode of the export of the Kriging models is unavailable at this time. So, well, that looks like it. We covered the 4 questions that came in. So thank you all for your time today, and again, please do stop by our booth at SciTech if you're there. Again, this webinar will be available on techplot.com/webinars, and if you want to contact us, there are our email addresses. Thank you very much.
Thank you.